Hello everyone, I Rajni Prashar welcomes you all to the lecture series of KEC 053 with the subject name VLSI technology as per AKGEC syllabus scheme. This subject is basically dedicated to the fabrication steps which we are going to follow in the processing steps of the fabrication of any IC, right. So in the previous lectures we have created the silicon crystal with the help of CZ process, and then with the help of oxidation your oxidation layer will be grown, and with the help of photolithography process we have created some windows where we have to diffuse some atoms or another impurities, right. So in this lecture, in the upcoming lecture, 2 lectures, we are going to familiar with the next processing step, that is the etching. The windows where we have created we have created with the help of photolithography process. From that windows we have to etch the silicon dioxide layer, and below that silicon dioxide layer in the silicon we have to dope the impurities, right. So, 2 types of etching will be used. We are going to use, the first one is the wet chemical etching, and this lecture is dedicated to the wet chemical etching technique. So, lithography is used to transfer the mask pattern onto the silicon wafer, and the next processing step will be your etching, right. The etching simply means to etch something from the pasted surface. If you have something pasted over the surface and you need to etch, you need to extract that thing so that you are in contact with the original surface, okay. So, silicon dioxide is etched because we know that we have this silicon substrate, right. We have created the silicon substrate, right, and with the mask we have created some windows. And from this side, over these sides, we have to remove the SiO2 layer, right. So, the silicon dioxide, let me change the pen. So, from these sides we have to remove the silicon dioxide so that we can diffuse the dopants in these areas, okay. So, silicon dioxide is etched by the dilute hydrofluoric acid solution with the deionized water. So, sometimes a buffered hydrofluoric acid solution can also be used, where a very much measured quantity of ammonium fluoride and hydrofluoric acid is used, which will give you a very controlled etch rate, that is your 1000 Armstrong per minute, okay. So, if you use a very much controlled process of etching, we can have the etch rate, that is 1000 Armstrong per minute. So, the steps which we are going to follow in any wet chemical etch step, the first one will be your transport. You need to have some liquid material which will work as a etchant solution, okay. So, the transport of etchant material to the surface, surface where we need to etch something, it should be there, right. So, we have this substrate, right. We have this substrate, over this we have the silicon dioxide, and from some sides we have to remove the silicon dioxide. So, the very much first thing is we need to have some container where your etchant solution should be there, and it should be transported to the surface of this substrate, right. And the etchants are usually in the solution form. Now, suppose you have this etchant solution in this beaker and you put the substrate in that, right. So, what will happen there? Your solution will come in touch with the SiO2 layer, right. So, one thing we should understand here, that the moment the solution comes in touch with this layer, it will form some stagnant layer, right. So, and the concentration at this side and at this side will not be same. So, for example, let us say my silicon dioxide surface is immersed in the hydrofluoric solution. This acid will react with the silicon dioxide, and if there is no fresh HF solution, it will not properly etch the silicon dioxide layer. So, the first important thing is a fresh HF solution should be provided. Okay, so the first thing is the fresh HF solution should be provided. It should not this solution should not be in the stationary phase. It should be stirred continuously so that we can have the fresh solution. It should be supplied from the outside. It and the concentration gradient inside this beaker should remain same. The silicon dioxide surface that has got depleted, the HF supply from the HF supply. So in order to have the continuous reaction, so that we can have the continuous etching process, the continuous supply of etchant material should be there. Okay. Now the concentration of this etchant solution is not exactly the same everywhere, right? I have already told that we have a beaker, in that we have the etchant solution, and in that we have put the substrate, right? So where the your etchant solution react with the surface, there your concentration gradient will be different, and in the rest of the portion your concentration gradient will be different, right? So to transport the etchant, the diffusion of the etchant through this stagnant layer is done, and they can come to the surface that is to be etched. And the second step here is the reaction is going to be limited. Okay, so the reaction, second thing is the reaction will be limited, means this means that which phase we are going to use for the etching, whether we are using 111 phase or we are using 100 phase, right? So depending upon that phase, your reaction rate will be different. And generally the crystalline material, in the crystalline material, the etching may be anisotropic, and when the etching is where the etching is dominated by the reaction rate. And isotropic term we will discuss in the later slides. And the third step from here is the mass action law. With the help of mass action law, we should know that if we need some reaction to be in continuous phase, the residual products, the unwanted products should be taken away, right? So to taken away that extra products, we need to stir the solution continuously, so that the uniformity of the etching will be there. So this stirring is going to serve both the purpose, that is your first purpose and the third purpose. First purpose was when you're so that it can maintain the concentration gradient constant, and the third purpose where with the help of stirring we are going to take away the residual products. So we have seen that this etching of silicon is done in a two-way process. The first step is your silicon is converted into silicon dioxide. This process is very much analogous to your anodic oxidation reaction. And the second step is you have to etch that silicon dioxide. Okay, and the very much common etchant solution that is used to etch the silicon dioxide is known as HNA. This is one important etchant solution, where your H stands for hydrofluoric acid, N stands for nitric acid, and A stands for acetic acid or aqua, that is your water. So different etching processes are selected depending upon the particular material to be used, which material we are going to etch. So depending upon that material, your etching process can be different. Wet chemical etch process result in isotropic etching, whereas both in case of isotropic etching, both vertical and lateral etch rates are comparable, whereas in case of dry etching process, the example of dry etching process is your sputtering etching, plasma etching, ion beam etching, reactive ion etching. So these are the example of anisotropic etching, and among the dry etching technique, your plasma and the reactive ion etching are the most popular semiconductor techniques. So this is the example where we can see the anisotropic etching and isotropic etching. So see, we have this layer which is to be etched, that is generally the SiO2 layer. Okay, so we have this layer which is to be etched from this side to this side. Okay, from here to here we have to remove this etch. So if the case is of isotropic etching, if we are using wet etching, so this wet etching not only etch this side, it will slightly etch from this side also. right? Whereas in case of anisotropic etching, we are going to have a very sharp etching edges. Okay. So next, in case of under this plasma anisotropic example, we can have this. We can see here also we have the very much sharp etching edges. And but in case of this, if you use the same material for with the help of wet isotropic etching, this material will be etched like this. Okay. So some under this cover, we are going to etch the material also. Okay. So isotropic, the definition of this isotropic and anisotropic etching: when the material is attacked by the liquid or or vapor etchant, it is removed isotropically uniformly in all the direction. Okay, so your isotropic etching. So here we can see that your isotropic etching is not only working in the vertical direction only, it also works in horizontal direction, right? So it works in both the directions. So it works in uniformly in all the directions. Okay, and in case of anisotropic etching, it works only in vertical direction, right? We have seen in the previous slides, it works only in the vertical direction. Here you can see the example of anisotropic etching. Here it is partially anisotropic etching and it is the isotropic etching. Okay, so it is the isotropic etching. So the material removal rate for wet etching rate is usually faster. Your wet etching technique is taken place at a very fast rate, whereas in case of dry etching, it may take some time, but your etching will be very much proper. So what are the chemicals which we can use in the wet chemical etching? Wet chemical etching is employed for the various processing steps. In wafer fabrication, your chemical etching is used for the lapping, polishing, or to give a optical flat damage free surface, which we have covered in the first unit, right? When you form the wafer, when the silicon ingot is formed and it is cut into the slices, that slices are then polished and lapping process is done, so that we can have a very much optical flat surface which is which will be damage free. And prior to that thermal oxidation or epitaxial process, these wafers are chemically cleaned, scrubbed to remove the contamination that results in handling and storing the wafers. For many discrete devices and integrated circuits of relatively large dimension, that is your greater than 3 micrometer, the chemical etching is used to define the patterns and the windows in the insulating material. So here we can, in this diagram, we can see that we have the three step. Etching is a 3-step. The first one is the transport of material. Okay. So first the transport of the material should be there. Your etchant solution should come in picture it should come in contact with the silicon dioxide layer. The second step is where you at the surface of silicon dioxide, your chemical reaction will take place. And the third step is, with the help of this stirring process, we are going to take out the extra products, right? So anisotropic in case of anisotropic wet etching, some specified chemicals are used. Liquid etchants etch crystalline material at different etch rate depending upon which phase of crystal we are going to etch. So there is a large difference in etch rate depending upon the crystalline plane. And in materials such as silicon, this effect can allow very high anisotropic rates. Some of the anisotropic wet agents are potassium hydroxide, that is named as KOH, ethylene, diamine, pyroxylate, EDP, or tetramethyl ammonium hydroxide, TMAH, which is commonly named as TMAH. So here we can see that when you have some different orientation, see, this is the profile for 100 orientation when we have the anisotropic and isotropic etching profile, right? So we have the same 100 orientation, but here in case of anisotropic profile. We have we are going to have this kind of profile, and this angle is very much important. Always this will be etched at 54.7 degree, and in case of isotropic, it is going to be in all the direction, in vertical as well as in horizontal direction, inside the silicon dioxide layer, right? So this is the example of isotropic when 100 plane is etched. So this second figure is the potassium hydroxide based wet etching, the first figure, and the second figure, it is when it is these are etched at the nanoscale. So the relationship between the mask dimension, etch depth, and the floor width is given by the equation D is equal to capital D minus 2H tan 54.7 degree, right? This 54.7 degree is this angle. Okay, this angle in case of anisotropic etching. So for semiconductor materials, some of the chemical reactions will take place during the etching process that we are going to cover in these two slides. So for silicon, most commonly used etching solution are your nitric acid HNO3 and hydrofluoric acid HF in water, or acetic acid CH3COOH. The reaction is initiated by promoting the silicon to form its initial oxide state to a higher oxidation. Okay, so your first step will be your silicon will be reacted with the hydrogen ions. These hydrogen ions are produced by K potassium this nitric acid. Okay, so with this this HNO3, it will be reacted with HNO2. This HNO2 is extracted from here itself. It will be split into 2 NO2 minus negative ions of this plus positive ions of hydrogen and water molecules, right? So these it will react with the silicon to have the more silicon. Okay, so this negative ion plus this hydrogen ion, positive ion of hydrogen, it will again give you HNO2. So from this reaction we can observe that this nitric acid is not going to be consumed, right? Whatever the nitric acid is used in this reaction, it is again regenerated from this reaction. So it is named as catalyst. It is named as catalyst part. So this silicon will be positive ion of silicon will be combined with the OH ions by the dissociation of water molecules to form the SiOH2, which subsequently liberated H2 and to form the silicon dioxide. So finally this silicon dioxide is formed. Now we are going to extract this silicon dioxide. Okay, so from this silicon dioxide is formed. It is then dissolved in hydrofluoric acid. So after this hydrofluoric acid, we are going to have, when the silicon dioxide react with hydrofluoric acid, we are going to have H2SiF6 with the water molecules, and the overall reaction will be written as this. So at a very high hydrofluoric acid and a low nitric acid concentration, the etching rate is controlled by HNO3. We have seen here that the HNO3 controlled the reaction. It is the only part where with the help of that we are going to generate the silicon. So because there is an excess amount of HF to dissolve any SiO2 formed. So at a lower HF and high HNO3 concentration, the H rate is controlled by the ability of hydrofluoric acid to remove the silicon dioxide when it begins to form. Okay, and in the later etching mechanism, your isotropic, that is not sensitive to the crystallographic orientation, it will be carried out, and the etching of insulating and the metal material is usually performed with the same chemicals that dissolved with these material in bulk to form and involves their conversion into soluble salts and complex. So this in the last slide we can see that these are the materials which we are going to etch. These will be the etchant composition and this will be the etch rate at a particular temperature. Okay, so for example, if we are using if we have to extract the silicon dioxide, then the etchant that will be used will be hydrofluoric acid, water, H4 NH4F, hydrofluoric, potassium, okay, potassium nitric acid, sorry, water molecules. So this will be used to etch p-type material, and this is used as a buffer hydrofluoric acid. So with this etched composition, the etch rate we are going to have is 100 nanometer per minute. Okay, so next, for example, we have the Si3N4 silicon nitride. These two are the etchant solutions, and for aluminium, all these will be used as a etchant solution. Similarly, we can have this list for tungsten. We can have the water molecules K, H2PO4, KOH, K3Fe, FeCN6. These all so we have the different, we can see that we can observe from this slide that we can have the different etchant compositions, so that we can etch the different materials, and with the help of each different composition your etching rates will be different. Obviously these etching rates will depend on the type of etching, which we are going to use, and the second thing is the orientation, right? Orientation of the crystal which is going to be etched. So thank you so much for this lecture. So in this lecture we have covered the etching process, what is the need of etching process, why we have to etch some material. We have to etch some material so that under that window we can come in contact with the original silicon wafer, and over that silicon wafer we are going to diffuse some of the impurities so that we can have the MOSFET, P-type or N-type MOSFET depending upon the requirements. So in this lecture we have also learned the isotropic and anisotropic etching and how the wet chemical etching works. This is done in the today's lecture. Thank you so much.